Today I'll talk about the implicit bias of optimization algorithms in deep learning. Actually, in the first talk this afternoon, Professor Li have introduced some similar properties about this topic, and here I'd like to introduce the implicit bias in deep learning either. First, let's look back to the classical learning theory. And in classical learning theory, the model, we usually use the linear model. And the loss surface is convex, and the problem is underparameterized. There is only one global minimum. So optimization algorithms is guaranteed to converge to the global minimum. And for the generalization side, we usually use the capacity of the hypothesis space to characterize the complexity of the model. So optimization and generalization are studied separately in classical learning theory. In the deep learning era, the loss surface is highly non-convex, which makes optimization may converge to different local minima or different global minimum. And the learning problem is over-parameterized. That means the model size is very big and much bigger than the number of training data. So traditional learning theory cannot explain why optimization algorithms can converge to a well-generalized solution. And it also cannot explain why different optimizers or different initialization will perform different on the test set. So new theory is needed for deep learning. And here are some examples to show how optimization and generalization interact with each other. The left two fingers shows that deep neural networks trained by specific optimizers such as stochastic gradient descent, even without explicit regularization, can find good solutions. And without the explicit regularization term, they can also find a well-generalized model. And the right finger shows that different optimizers, such as stochastic gradient descent or ADA-grad, will converge to different solutions, and they perform differently on the test data set. This indicates that the optimizer itself shows implicit bias when they optimize the deep neural networks. To characterize this implicit bias, we usually aim to characterize the complexity of the converged point of a specific optimizer, such as gradient descent. For example, flatness or margin can be used to characterize the complexity. In 2018, Sodri firstly tried to formulate this problem, and they proved that gradient descent can converge to the max margin solution on the separable data under logistic regression settings. And after that, there are many followers to develop this kind of theory, and both for the classification problem or regression problem, the implicit bias of gradient descent are characterized for both over-parameterized linear model and two-layer neural networks or deep linear networks. But it is still very challenging to extend this kind of theory to general deep neural networks. Here I'd like to highlight a remarkable breakthrough, which is done. The work is done by Lyu and Professor Li. They extend the theory to deep neural networks, but with a nice constraint. That is the homogeneity. Homogeneity means if we scale the parameter of the neural network by a scalar, and its output will be scaled accordingly. And fortunately, many types of deep neural network satisfies this kind of property. For example, the convolutional neural network with ReLU or leaky ReLU activations, or pooling and weight normalization. They both, all of these kind of neural networks satisfy the homogeneity. And why homogeneity is a good property? Let us look at the margin maximization solutions. It is related both the training loss and the norm of the parameters. And with homogeneity, the decreasing rate of the training loss and the increasing rate of the norm will be bridged. And with this property, they prove that gradient descent can converge to the max margin solution on the separable data on this kind of deep neural networks. And when we first look at learn this result, we felt very excited because we think this mathematical tool may help us to answer some questions. For example, there are many other concepts connect with generalization in an optimization problem. For example, preconditioning in the adaptive optimization algorithms, or momentum and gradient noise. All of them will influence the generalization performance, and we think the margin theory can help us to evaluate how these techniques will influence the generalization, and we like to develop the theory to other types of the optimization algorithms and give them a measure in terms of the generalization in deep learning. Next, I'd like to introduce two of the works from our group, and which is collaborated with PhD candidate Bo Han and my colleagues Wei Huishuai, Tian, and under supervised by Professor Ma. First, let us revisit the margin theory and the generalization. For a linear classifier, the margin is defined as the product of the label and the inner product of the normalized parameters and the input. Geometrically, the margin measures how separable of the training data. And a lot of work have shown that larger margin can guarantee good generalization. And the margin maximization problem is equivalent to solving the following constraint optimization problem. And extending it to deep neural networks, we can just replace the linear model with the deep neural network, which is denoted as FNN. First, we'd like to study the preconditioning in optimizers, and its update rule, the general update rule for optimizers with preconditioning update the parameters along the negative direction of the gradient vector with a preconditioned matrix denoted as HT. And there are many examples. For example, the ADA grad AMS prop ADAM, these adaptive optimizers have a preconditioning matrix, but their formulation may be very different. And we want to answer why this optimization algorithm perform very differently. In order to connect these optimization algorithms with the margin theory, first, we propose adaptive gradient flow to put them in a unified framework. And all the three optimizers are special cases of this adaptive gradient flow. And the beta t in the adaptive gradient flow should be satisfied that their limit they both approaches to the unit vector. Second, we study the convergent direction of the adaptive gradient flow and propose surrogate margin. How to construct this surrogate margin? First, we need to find a lower bounded term, and this term should be both related with the loss function and the norm of the parameters. We can prove that this surrogate margin is lower bounded, and by using it, we can bridge the decreasing rate of the loss function and the increasing rate of the model parameters, the norm of the parameters. Finally, we study all these three optimizers, and we study the limits of their preconditioners, and we can obtain their convergent direction. With the homogeneity and the margin theory, we can get our final result. It states that if the limit of the preconditioner in an optimizer is an isotropic vector, the optimizer will converge to the max margin solution. Here are some examples. For IMZ prop and Adam, they will converge to their preconditioners will converge to a unit vector. So they can converge to the max margin solution, which has low complexity and has generalization guarantee. And for other grad, it's the limit of this preconditioner is anisotropic. Therefore, in practice, it performs worse than the other two optimizers. We also evaluate the margin under different initializations, and it shows that other grad converges to different directions, and its direction is very sensitive under different initializations, which matches our practical implementations. Besides preconditioning, we also care about how momentum and gradient noise will influence the convergent direction of an optimizer. Next, I'll introduce our study on the stochastic gradient gradient descent with momentum. The update rule for momentum SGD has an extra term compared with SGD itself. And this extra term is related to historical gradient. And this term makes the loss cannot be guaranteed to be monotonous decreasing. To deal with it, we need to construct a new Lyapunov function to analyze the momentum SGD. And actually, the convergence theory in optimization of momentum SGD is also not well studied. And here to analyze it, first we use an equivalent update rule for the momentum SGD, and then we construct the Lyapunov function as the expectation of the loss function at the auxiliary variable ut, and we can prove that the upper bound of expectation of our ut is monotonously decreasing, and we can use it to prove the summation of the historical gradient is upper bounded, which is a bridge for us to get the convergent direction of momentum SGD. Finally, we can conclude that if the learning rate is properly set, as the momentum SGD will also converge to the max margin solution. That means momentum and gradient noise will not influence the convergent direction of an algorithm. Finally, let me summarize In this talk, we studied the implicit regularization of preconditioning, gradient noise, and momentum. And we studied the condition for them to converge to the max margin solution on a homogeneous deep neural network with separable data. And in future, we'd like to study how batch size will influence the generalization in deep learning. And we aim to design robust optimizer for large batch training, which is required in some practical scenario. Thank you, and I'd like to show special thanks to my collaborators, Bohan Wei, Hui Shuai, Ruoyu Tieyan, and Professor Ma. Thank you.